Finally, in this series of simple circuit videos, we'll deal with networks of resistors, either in parallel or series. Resistors in parallel, you can see, are joined to two different nodes in your circuit. That means current flowing from the positive end of the battery will split at node A. One amount of current I1 will pass through resistor 1, and a different amount of current I2 will pass through resistor 2. We will apply Ohm's law in this derivation, and what we would like to know is what's the equivalent resistance of these two resistors in parallel, and we'll generalize to any number of resistors in parallel at the end. The voltage, of course, has to be the same for any circuit element in parallel. We saw that for capacitors, and of course it's true for resistors as well. So the battery voltage is equal to V1 is equal to V2. Ohm's law gives us that IR for the equivalent circuit will equal I1R1 and will equal I2R2. So we have this proportionality between the currents and the resistances, but we must now apply this concept that all of the current going into a node must come out. So whether you look at node A or node B here, current total I passing into node A equals the sum of the currents leaving node A, I1 plus I2. You could look at node B, but it just gives you the same information, that I1 plus I2 coming into the node equals I leaving the node. So you see, given our relationship between total currents and eliminating current I1 from the expression using the equal voltage relationship at the top, we have that the equivalent resistance here, with a little bit of algebra, is the inverse of the sum, is the inverse of the sum of the inverse resistances. And this simple case for two resistors generalizes for n resistors in parallel, so that the inverse of R1 plus the inverse of R2 plus ... the inverse of Rn, all of that inverted gives you equivalent resistance. And just like we saw for capacitors in series, the equivalent resistance will be smaller than the smallest resistance that goes into this parallel configuration. And of course, now you can see that the math is opposite for the rule that we got for capacitors in parallel. That was just simple addition of the capacitance. So if you go and look at the resistors in series, this is the simpler computation. Resistors that are in series must have the same current flowing through them. They're on the same branch of the circuit. There's no nodes for that current to split at. In this simple example, we have the current flowing clockwise. We apply Ohm's law with the information that the current is the same for each resistor in series. And we can see that the ratio of the voltages must equal the ratio of the resistances. Recall that's now opposite of what we saw for resistors in parallel when we had the ratio of I1 divided by I2 is the inverse resistance ratio. Now that would be R2 over R1. Here the voltage ratio is the resistance ratio, and we have to apply the idea of conservation of energy so that the voltage drop around your loop must be zero if you return to the same point in your circuit. This demands that the voltage drop across resistor 1 plus voltage drop across resistor 2 equals the battery voltage. We insert Ohm's law, V equals IR for the equivalent case, IR1 plus IR2. Since they all share the same currents, we've recovered the result that we want, which is that the equivalent resistance is the simple sum of the individual resistances. R1 plus R2 plus so on up to Rn for any number of resistors in series. And you see again that the rule for resistors in series is opposite of the rule for capacitors in series.